I'd like to thank the organizers for the opportunity. So today's topic is holomorphic symplectic geometry of elliptic surface. The joint work with Guolei Zhong, who is in my center. So in this talk, I consider symplectic structure in the holomorphic sense. So when we say a holomorphic symplectic form, and we only consider this on a surface, on a complex surface. This just means just a nowhere vanishing holomorphic two form. So, and just to make things simpler, I will not use holomorphic. So from now on, when I say symplectic form, it automatically means holomorphic symplectic form. And so when you have such a symplectic form on a complex surface, you can study symplectic geometry of the surface. And this, somewhat surprisingly, hasn't been studied very much. And so today we'll study this on elliptic surfaces. And elliptic surface means a surface with elliptic fibration. So let me recall the definition. So an elliptic fibration which I will abbreviate by EF, elliptic fibration, is, what is elliptic fibration today is the following, where X is a complex surface and C is a Riemann surface, and F is a proper surjective holomorphic map. And sigma is a section. So this is what I mean elliptic fibration. There are other definitions, but for today we'll use this definition. It's one missing of such that the Zariski open set we consider the following elliptic. This is defined as points where the fiber is an elliptic curve. Is non-empty. So it's a fibration of surface over Riemann surface such that general fibers are elliptic curves. And we assume there's a section to simplify the theory. Okay. So that's what I mean by by elliptic fibration. And if there's a symplectic form omega on X, we call it a symplectic elliptic fibration. And we abbreviate it by SEF, symplectic elliptic fibration. So that is the terminology. So symplectic elliptic fibration just means elliptic fibration with some additional two form, symplectic form here. Okay. Now some more terminology. So for two symplectic elliptic fibrations, so consider, so one is So you have one symplectic elliptic fibration and another. So we have two such. Then we say that, first of all, a biholomorphism is elliptic fibration isomorphism if the following obvious properties holds. If it sends the section to section and phi descends to biholomorphic. And okay, that's it. And if furthermore the pullback of it preserves the symplectic form, then we say it's symplectic elliptic fibration isomorphism. Okay. So it's an obvious definition. Isomorphism in the sense of elliptic fibration, and isomorphism in the sense of symplectic elliptic fibration. So it's obvious. Now we need a slightly more involved concept, and this is the following. So a meromorphic map psi from x to x tilde is on symplectic elliptic fibration isogeny. So this is the terminology I like to define, isogeny. If it descends to a surjective holomorphic map, okay. So let me such that the following holds. So let me draw some picture to help. So here, so this is this elliptic fibration, and here maybe here you have another. So this is sigma, and this is sigma 2. So another elliptic fibration, and isogeny, SEF isogeny is a meromorphic map. It's a meromorphic map, which induces a surjective holomorphic map down there, and such that for all general point, there's a neighborhood. And there are neighborhoods of y for general point y. There are neighborhood O and O tilde such that psi restricted to the inverse image is first of all is a biholomorphism, and this is SEF isomer. So if you at general point, if you restrict to some neighborhood, then over there you have some. This is pretty restricted to. So at each point you have some neighborhood, which over which they are just biholomorphic and such that it is SEF isomorphism. So in terms of it's symplectically equivalent. It's biholomorphism preserving the symplectic form and also the section. So it's a somewhat more involved concept, sort of generalizing isomorphism, SEF isomorphism to map, to meromorphic maps. So that is the concept. So any question about the definition? This concept is very important for us throughout today. This in particular means the meromorphic map has all the bad loci inside the fibers. All the bad loci, exceptional sets are all inside the fibers. So generically, it's like locally isomorphism. Okay. Now we recall this another definition. This is Kodaira's J map. It's defined as follows. For when you have elliptic fibration, now you have this open set where the fibers are elliptic curves. Then you have the holomorphic map from this open set to M. M is the moduli of elliptic curves. So in this morning, Naiming's lecture, we saw that this is the quotient of upper plane by PSL to G. So this is biholomorphic to C. And you have a natural map for each point in this open set. You have the fiber. The fiber is an elliptic curve. So it's a point in the moduli elliptic curve. So you have this map. And what Kodaira proved was that this map can be extended to a holomorphic map, J, from C to M bar, which is a compactification of the moduli space. So this is a compactified moduli of elliptic curves. And so this map extends to a holomorphic map from the whole C to the compactified elliptic curve. So this is called the J map of the elliptic fibration. This elliptic fibration. So each elliptic fibration has induced this holomorphic map. And we say that this elliptic fibration is non-isotrivial. If J is not constant. Okay. So we define J map and non-isotrivial. And in this talk, we will be only interested in non-isotrivial elliptic fibrations. There are something we can say for isotrivial case, but let's concentrate on non-isotrivial case. Now, as a motivation, why I started working on this subject, I had the following question. So let me recall this motivation. So I looked at K3 surfaces. With non-isotrivial elliptic fibrations. And there are many such, many. So in fact, it forms 18-dimensional families. So and in this case, the base Riemann surface must be P1. So any elliptic fibration of K3 surface is over P1. And which means that J map is from C to M bar. This must be surjective. It's a non-constant holomorphic map from P1 to P1, so it's surjective. Now, what is the problem? The problem is the following. So, pick any two such let's pick, there are so many, so just pick any two. So let me see, I draw the picture like this. So let me try to. So this is one K3 surface. This is another one with the elliptic fibration. And we have J map to M bar. And they are all surjective. J maps are all surjective. Then you can see that you can always find some open set such that this is biholomorphic. So O1, O2, J01, J1, O1. So you can always find a small open set. They are all biholomorphic. O1 in C1, O2 in C2, such that they are biholomorphic by J. By the composition of J map. This always happens. Now, if you look at the inverse image of O1 and O2 here, so here we are considering also sections. Sigma. Now, in this situation, there is a unique biholomorphic map. This is unique up to plus minus the flip, the reflection by -1. Biholomorphic map P from because they are the same family of elliptic curves. On O1 and O2, they are sent to the same moduli of elliptic curves. So they are identical family of elliptic curves. So there is a biholomorphic map. So this is an EF isomorphism. So this is true for any two choice of such K3. It's always true. Now the question is, since on K3 surface, the holomorphic 2 form is all generated by some symplectic form. And these are symplectic forms. So the question I had was this. Maybe here. The question. Was whether this unique isomorphism, so this isomorphism from this open set to this open set, whether this unique isomorphism sends omega 2 to omega 1 for some C. So that's the question. So whenever you have two such cases, you have this kind of open set, and you always have a unique bi-holomorphic map. And the question is whether this is also a symplectic map. So is P or SEF isomorphism? So that is the question. And this question I asked a few experts in K3 surfaces, like Guolei Zhong. And they say that they don't know. They don't know the answer. So I was curious what's true. And we tried to give an answer to this question. Yes?
For Mr. Cohen, how important is this section?
For my result, I state it's important to simplify things. But without section, you can state something. But let's not discuss it. May I say, not too important, but it's important for today. Okay. Now let me give you, first of all, let me state the result as an answer to this question first. The theorem. Answer to question. The following. So first, if, suppose the answer is yes, and we can choose C just one. So if this is true, then there's another case with, so which I write this. There's another case with elliptic fibration. So and SEF isogenes X1, X2, there's isogenes PC1, PC2. So if this phi is symplectomorphic, then there's always always two isogenes, and such that this commutes. So here also C1. So this is the answer. So this happens only when something globally happens. Okay. So this is a local state, local equivalence, which always exists for any case of this type. But if this becomes symplectomorphic, then it automatically comes from some global maps. Okay. So in other words, local SEF isom can be extended to a composite of two isogenes. So something which is purely locally defined actually comes from some global equivalence. So that is the first answer. Now, well, but the thing is, this cannot usually happen between, if you pick two general cases, this cannot happen. So that's the second point. So this I stated slightly vaguely. If X1 and X2 are sufficiently general, then occurs only when they are actually biholomorphic, and phi is the restriction of biholomorphic. So it comes from biholomorphic automorphism. In other words, the answer is usually no. If you pick x1 and x just generally, this map cannot preserve the symplectic form. So that's the answer. And when it preserves symplectic form, x1, x2 has to be in a very special relation, which comes from 1. So that's the answer to the question. Okay. Now, how do you prove something like this, answer something like this? Especially what's curious is what is this guy? When you are given two K3, x1 and x2, you suddenly obtain a third K3 here. So what is this? So where does it come from? So that's I know. The another one is also filled. The another one is also filled, unfortunately. Where's my? I brought my eraser because the eraser I'm not so familiar here. Actually, this is not very pretty. Okay, so where does this third guy come from? This is the content of the next theorem. So this is our symplectic reduction. It's the following. So over there, it's about K3 surface, but here it's about any symplectic electric fibration. So given a non-isotrivial symplectic electric fibration, so sigma x, there exists a unique of the natural isomorphism, unique symplectic electric fibration, which we write as sigma hat x hat. So associated to any symplectic electric fibration is another one. That's the same symbol as this. So that's the guy. This is called the symplectic reduction of x. So here you are defining this concept, symplectic reduction. And it has the following property. With the unique symplectic electric fibration isogeny, which is Xi from x hat. Such that for any SEF isogeny, so from X, so suppose you have an isogeny from this to another symplectic electric fibration. Then these factors sigma. So in the sense that you have psi x hat and here also. So if you have any isogeny, it must factor this isogeny, the symplectic reduction. So in other words, SCF isogenies with a fixed source has a universal object. And that is the universal object is the symplectic reduction. So that's the nature of this guy that appears. So this guy x hat to c hat is a symplectic reduction of both x1 and x2. And these two isogenies are just symplectic reductions. So that is so this is the main theorem actually. So given any symplectic elliptic fibration, you have some kind of universal object which absorb all isogenies. Now let's use the second. Okay, maybe I will. The same, okay. Any question so far? The blackboard? Well, what is the question? Let me clean this because this is not very effective. So let me. I know. I'm very sorry. If there's a better name, I know. This is the terminology I cooked up. So if there's a better terminology, please suggest. Please suggest. Because it's kind of locally, it's very similar to symplectic reduction. Locally, it's reduction by some finite group action. Yeah, it's hidden there. It's locally there. There's no global action, but there's some local action.
What do you mean sufficient?
That can be interpreted in many ways, but in our result, we can prove at least if they have Picard number 2, which is the general Picard number of elliptic K3, and if all the singular fibers are I1, the simplest type, then this is true. So in that sense, you can give a more precise meaning to this, but I think our result is not optimal. There must be more precise result. So at the moment, it's just sufficient. It's sufficiently general in the sense it's very general point in the moduli of elliptic K3. Okay. Now let me give you the idea behind this construction of symplectic reduction. Because if you understand the idea behind the construction, then you can understand how this theorem can be proved. There are a few concepts, but I think the most important one is this what's called action angle theorem, which is very classical, maybe due to Liouville. I don't know exactly who. Sometimes people call it Arnold-Liouville theorem, Liouville-Arnold theorem. It's something like this. So suppose you have elliptic fibration, but this is now smooth elliptic fibration. Smooth EF. Well, why I use this? Sorry. So you have a smooth elliptic fibration. This means that all the sets, all fibers are elliptic curves. Then there is a canonical unramified surjective holomorphic map. Chi from the cotangent bundle of the Riemann surface to X, such that this sends the zero section to the given section, and the pullback of the symplectic form is the canonical symplectic form. On the cotangent bundle. And also for any point, the restriction to the fiber is the uniformization over the elliptic curve. So in particular, the inverse image of the section is a lattice. So this is the definition of this lambda. So lattice, such that if you take this quotient, this is isomorphic to the elliptic curve y. This is the theorem. It's actually not too difficult to prove now, but perhaps when it is first observed, it's extremely intricate result. But now, if you know the statement, you can prove it. Actually, if you, this map is there's an obvious such map. Okay. Now the second ingredient, which is, I think, somewhat original in the sense that it's something elementary, but somehow people didn't thought about it. And this is bundle of tautological lattices. So this is another concept which is useful. So what we do is, for each point in the moduli of elliptic curve, so this is moduli of so for each point, which is an elliptic curve E, let's consider the following. L, E, this is defined as follows. This is a set of lattices inside the cotangent space of M, cotangent space of the moduli space, which is a lattice, such that when you take the quotient, this is isomorphic to E itself. So you consider all lattices inside the cotangent space of the moduli space, such that the quotient becomes exactly isomorphic to the elliptic curve itself. Then you can see that this is isomorphic. This set is isomorphic to C star modulo automorphism of E, the pointed elliptic curve. So now let M0 be the moduli of elliptic curves with automorphism, with a trivial automorphism. Just plus minus 1. Then this is an open set. This is an open set. And this is biholomorphic to C minus 2 point inside C. So C is, so inside the moduli space, you just remove 2 points. Then the general elliptic curve without complex multiplication is just trivial automorphism. And then now you have this bundle. L is defined as union of this LE over this open set. And this is now a C star mode plus minus 1 principal bundle. So you have a natural principal bundle over this open set in the moduli space, consisting of just lattices, which give the corresponding elliptic curve. So this is called I will call it the bundle of tautological lattice. It's lattices which have a tautological property. Okay. Now, then the third ingredient, which is most important, this is a lambda map. This is the following. So now you recall that there's J map associated to any elliptic fibration. Now there's some map associated to symplectic elliptic fibration. So for non-isotrivial symplectic elliptic fibration, we have this J map. Let C0 be the open set of the points of smooth fibers such that Jy is in M0 and J is unramified at Y. So let's consider this open set in the base where the J map has values outside this bad point, and then J map is unramified at that point. So that is the open set C0. Now you define the following holomorphic map. Okay. Then for each point in the C0, we have this map. The restriction of the elliptic fibration to C0 is this is a smooth. Over this open set, this is smooth. So we have lambda y inside Ty star C by 1. 1 is behind, is it? by one action angle theorem. By one, there's a lattice inside the cotangent space of C, because it's a smooth symplectic electric fibration, such that this, okay, and then one more. Now, J is unramified at Y by our choice of C. J is unramified. So the derivative gives an isomorphism from C to the tangent space of the modular space. And so it sends lambda y to a lattice, lambda jy, inside cotangent space of the modular space. Because you have an isomorphism, it sends a lattice in the dual to a lattice in the dual. And this is inside the tautological, this is a tautological lattice, such that T star jy m lambda j is jy, namely xy. So this is inside lambda jy is inside the bundle of tautological lattice. So this defines a holomorphic map. Which factorizes J map. Sorry, this is error. So you have a factorization of J map to this bundle of tautological lattices, which is lambda. So this I will call the lambda map. So if you recall, J map from C to M bar is determined by the electric fibration. Now you have this lambda map, which is from C0 to L. This is determined by symplectic electric fibration. So this is an invariant of the symplectic electric fibration. It's given by a map. And this map, actually, one can prove the following. So this lambda map determines the converse is true. So lambda map determines the symplectic electric fibration. So in other words, the following is true. So if you have two non-isotrivial symplectic electric fibration, sigma 1, x1, sigma 2, if there is a biholomorphism which sends C10 to C20, and this lambda 1, there's a lambda 1 and lambda 2. And lambda 2 is, lambda 1 is lambda 2 P. Then, so if this is then, there is symplectic electric fibration isomorphism. Descending to. So this function, this holomorphic map from this holomorphic map lambda, it determines the symplectic electric fibration in the sense that if two symplectic electric fibrations have equivalent lambda map, then they must be isomorphic. And this is very different from J map. J map is determined by elliptic fibration, but J map does not determine elliptic fibration. You need monodromy information to determine it. But this lambda map determines, just the map itself determines the whole thing. So there's some, it shows that there's some advantage of using symplectic geometry. It simplifies even some part of elliptic fibration theory. It becomes simplified. So that's the result. And the proof of this is essentially is an application of this action angle theorem. Now, in the remaining 10 minutes, let me tell you how to prove the reduction, how to construct the symplectic reduction, and why we have results like this. Any questions? Okay, so let's see how one constructs the symplectic reduction. How to construct the symplectic reduction from so you are given any symplectic electric vibration. You want to associate another one, which is sort of simpler object, some kind of reduction. And the construction is that, and it comes with some isogeny, the universal isogeny. There's a that was the symplectic reduction. And first of all, this map. This is a closure, in a sense, is a closure of the lambda map. So what do I mean? I cannot define it precisely, but what you have is that you have this symplectic electric fibration, and inside here you have some open set, and here you have some this bundle of tautological lattices, and lambda is a map from C0 into here, and which may have some, so this is lambda. So you have some curve, some Riemann surface inside here. It may have a self-intersection, but essentially you have some Riemann surface inside this C-star bundle, which is, this is lambda map associated with this structure. And what we're going to do is that this map is not well defined outside C. So this is a closure across C minus C0. So the lambda is defined only on this some Zariski open set, but we can sort of take closure in a suitable sense. So that is what this map. And then this symplectic electric vibration, then we consider the following object. Just take all quotient. Now, by definition of this lattices, each point is a lattice in the cotangent space downstairs. So you have a naturally associated elliptic curve, elliptic fibration. So this lambda C0 has a natural symplectic elliptic fibration. There's a canonical, the tautological symplectic elliptic fibration, where each fiber over here is, this is just T star M JY modulo lambda JY. At each fiber, the point of L is a lattice inside the cotangent space. So you have a natural elliptic curve over there. So you have a tautological symplectic elliptic fibration over this. And it is symplectic elliptic, the symplectic structure comes from the cotangent space of the moduli space. And then you define X hat as a closure of X0 across C minus C0. So the main technical problem arises along in the neighborhood of the exceptional point, where outside this open set, where this fibration is not well defined, and there possibly can be a singular fiber, but there's a way to make a sort of completion at such point using some symplectic group action. That part I will not go into today. So this is how you produce symplectic reduction. And finally, let me say how the symplectic reduction implies this kind of result. When you apply to K3 surface, how the symplectic reduction applies. It's because in the setting of the question, this was the answer to question. In the setting of the question, you have this x1, to C1, and x2. These are K3 surfaces. And we had some open set, O1, and some, we look at the fibration over this open set, and we have this phi, and assume if this map sends omega 2 to omega 1. Then what happens? Let's look at what happens. Here's omega 1, and here's omega 2. So these are symplectic elliptic fibrations. Then the lambda map. So here you have L, and you have this bundle of tautological lattices. And you have this lambda map, which sends C1 to something here. So this is lambda C1. And then it also sends C2, this was lambda 1. It sends C2 to something. So this is lambda C2. They have lambda map. But the lambda map is invariant of symplectic elliptic vibration. And the symplectic structure on these two strips agree, which means that these two Riemann surface inside this bundle, they must share some open set. So the picture is funny, but this is lambda 1. Because they have the same symplectic elliptic vibration structure, their image must agree on some open set, which means that they actually agree everywhere. So this picture is not good, but this actually shows that this must be equal to lambda C2. So whenever you have some neighborhood of open set has the same symplectic structure, the image inside here must agree. So both must have the same symplectic reduction. So here psi1 and psi2 are symplectic reduction, and they must agree. So that's how this is proved. That's it. Thank you.
Thanks a lot.